Valvetronic engines use a combination of hardware and programming to abolish the need for a regular throttle mechanism. Valvetronic varies the lift of the intake valves, based on signals formerly taken mechanically from the accelerator pedal position sensor. The stepper motor changes the phase of the eccentric cam, modifying the action of the intake valves. This system is a conventional intake cam, but it also uses a secondary eccentric shaft with a series of levers and cam followers, activated by an electronic stepper motor. The Valvetronic engine replaces the function of the throttle body by using infinitely variable intake valve lift. Valvetronic has its own computer housed in a separate unit away from the engine management system, networked through CAN network with the digital engine management system incorporating a 40 MHz, 32 or 64-bit computer. Valvetronic was introduced on the all-alloy 1.8-liter, 4-cylinder engine for the E46 316 tons BMW. It is now applied to some 8 and 12-cylinder engines. The new E65 7 Series has Valvetronic engines. The entire Valvetronic system is pre-assembled and inserted as a module into its position in the cylinder head. Valvetronic engines are built near Coventry, England. Valvetronic reduces maintenance costs, lowers exhaust emissions, improves cold start behavior, and provides a smoother running engine. It also does not need specific fuel grades or fuel qualities because of its fine atomization of fuel. Because Valvetronic allows the engine to breathe unrestricted, fuel consumption is reduced by 15%. The fuel savings are highest at lower engine revolutions. With fuel injection systems, at light throttle, the throttle butterfly nearly closes, while the pistons are still running, taking air from the partially closed intake manifold. The intake manifold between the throttle and the combustion chamber has a partial vacuum, resisting the sucking and pumping action of the pistons and wasting energy. Automotive experts refer to this phenomenon as pumping losses. The slower the engine runs, the more the throttle butterfly closes, and the more energy is lost. Valvetronic minimizes pumping losses by reducing valve lift and therefore, the amount of air entering the combustion chambers. This system is now possible because of advances in technology. Compared with conventional twin-cam engines with cam followers, Valvetronic employs an additional eccentric shaft, an electric motor and several intermediate rocker arms, which in turn activates the opening and closing of valves. If the rocker arms pushes deeper, the intake valves will have a higher lift, and vice versa. Therefore, Valvetronic has the ability to get deep, long ventilation or a large valve lift, and flat, short ventilation or a short valve lift, depending on the demands placed on the engine. The operating parameters of the Valvetronic system are as follows. Valve lift is variable between and 9.7 mm. The cams controlling the eccentric shaft are machined to tolerances of a few hundredths of a millimeter. In Valvetronic engines, coolant flows across the head, resulting in a temperature reduction of 70%. The water pump size is cut in half, reducing power consumption by 55%. Adjustment of the worm gear from one extreme to the other takes 300 milliseconds. Combined with double Vanos valve timing technology, the camshaft angle relative to the crankshaft can be adjusted by up to 60 degrees. The efficiency of Valvetronic engines drop rapidly at over 6,500 revolutions per minute, since stronger valve springs are required. The stronger springs creates higher friction losses. So in essence, Valvetronic has its greatest benefit at normal and lower engine revolutions.